All right, let's talk about something that sounds, well, completely backward. When you think about space, you probably picture the absolute freezing cold, right? And you're not wrong. So it might be a little surprising to hear that one of the biggest, most difficult challenges for any spacecraft, from a tiny satellite to a future moon base, isn't about staying warm. It's about getting rid of heat.
It's this wild paradox. See, down here on Earth, we can get rid of heat pretty easily through conduction and convection, just passing it to the air or water around us. But in the vacuum of space, those options are just gone. The only way to dump all that waste heat is through thermal radiation. And when you start talking about the huge amounts of power we're going to need for future missions, this isn't just a small problem. It's a potential showstopper.
Just how big of a showstopper are we talking about? Well, for a typical power system in space, the radiators, those big panels or fins that radiate the heat away, can make up a staggering 30 to 40% of the entire system's mass. Imagine that. It's like finding out that for every 3 parts of your engine, you need another 2 parts that do nothing but cool it down. That is a ton of extra weight we have to blast into orbit.
And that's exactly why these traditional solid radiators are such a bottleneck. I mean, first off, they're massive and heavy, which makes them insanely expensive to launch. They're also super vulnerable. Just one tiny micrometeoroid hit can puncture a cooling loop and take the whole thing out. So what this all means is that our biggest dreams for space, bigger space stations, more powerful systems, they're being held back by these heavy, fragile panels.
This is where the thinking gets really, really clever. Engineers looked at this massive problem and they asked a truly brilliant question. What if you could just get rid of the solid panel altogether? What if, instead, you could use a liquid exposed directly to the vacuum of space to do the job? I know, it sounds like something straight out of science fiction, but it's an unbelievably elegant solution to a very, very heavy problem.
And that idea has a name, the Liquid Droplet Radiator, or LDR for short. The concept itself is beautifully simple. You use a free-flying sheet of millions of tiny liquid droplets as your radiating surface. They shoot through space, radiate their heat directly into the void, and then they're collected on the other side to be reused. No heavy panels, no delicate pipes, just a controlled, glowing mist doing all the work.
So how on earth do you actually create a giant sheet of liquid in the middle of space without it all just floating away? Well, the answer is in this incredibly elegant closed-loop system. Okay, so you can see the whole cycle right here. It all starts when the working fluid picks up waste heat from, say, a nuclear reactor or some power electronics. Then, a generator atomizes that hot liquid, spraying it out into this superfine mist, a thin, uniform sheet of millions and millions of droplets. As this cloud of tiny droplets travels through space, it radiates its heat away, cooling down really fast. And then finally, a collector at the other end catches all the now cool liquid, ready to be pumped back to start the whole process over again. It's just a simple, efficient loop.
And this is the punchline. This is the game-changing advantage of the LDR. For the exact same amount of cooling power, an LDR system can be 5 to 10 times lighter than a traditional radiator. I mean, in the world of spaceflight, where every single gram costs a fortune to launch, that is an absolute revolution.
Of course, going from a brilliant idea on a whiteboard to a piece of hardware that actually works in space is a huge leap. Engineers had to solve some incredibly tough challenges to even think about making this a reality.
First problem, and it's a big one, the liquid itself. I mean, think about it. Space is a hard vacuum. If you expose most liquids to that, they'll just instantly flash boil into vapor. So what in the world can you use? The trick is finding a liquid that has an extremely low vapor pressure, which is just a fancy way of saying it has almost no desire to evaporate, even when it's hot.
And it turns out there's no single perfect fluid. It really depends on the job. For relatively low-temperature tasks like cooling solar cells, a special kind of silicone oil works great. For medium temperatures, you might use what's called a eutectic, basically a metal alloy, like a mix of sodium and potassium, that melts at a way lower temperature than either metal would on its own. And then for the really high-power, high-heat stuff, like a nuclear reactor in space, you go straight to a pure liquid metal, like tin, which can handle temperatures up to 1,000 Kelvin.
Engineers also had choices to make about the shape of the droplet sheet itself. The two main designs are the rectangular LDRI and the triangular one. The rectangular design is pretty straightforward. You have a simple generator and a simple collector. The triangular version actually focuses all the droplets down to a single point, which requires a more complex collector but could be useful for different kinds of spacecraft layouts.
But honestly, the biggest challenge of all is the absolutely insane level of precision you need. The generator has to pump out millions of perfectly identical, perfectly uniform droplets. The aiming has to be so accurate that you avoid losing the liquid. And get this, over a 30-year mission, the acceptable loss rate is just one single droplet for every 100 million that are sent out. 1 in 100 million. And then the collector has to catch them all without a single splash. It's a truly mind-boggling engineering feat.
So why does all this matter? Why go to all this incredible trouble just to engineer a radiator made of liquid? Well, because solving this one problem isn't just about a small improvement, it's about fundamentally unlocking our future in space.
See, this isn't just about making things a little bit better or a little bit lighter. A technology like this is what's called an enabling technology. It could be the key that finally unlocks some of our most ambitious dreams. We're talking about things like sprawling bases on the moon, huge solar power satellites beaming clean energy back to Earth, and the next generation of massive space stations. All of these things require megawatts of power, and they all have to shed enormous amounts of waste heat, a job that LDRs seem practically designed for.
So, when you boil it all down, what's the real takeaway here? It's that developing these radiators isn't just some abstract engineering puzzle. This isn't just about saving a bit of money on launch costs. It's about making missions possible that are, right now, simply impossible. Lighter, more resilient radiators directly translate into more power. More power for science, more power for exploration, and more power to chase our biggest ambitions out there. It really leaves you with a pretty incredible thought, doesn't it? The key to building vast cities on the moon or giant power stations in orbit might not be a new kind of rocket engine or some super strong material. It might just be something as elegant and seemingly simple as a controlled, glowing shower of liquid metal radiating heat away into the endless cold darkness of space.